Let's rewind the clock. Before humans existed, before Earth formed, before the sun ignited, before galaxies arose, before light could even shine, there was the Big Bang. This happened 13.8 billion years ago. But what about before that? Many physicists say there is no before that. Time began ticking, they insist, at the instant of the Big Bang, and pondering anything earlier isn't in the realm of science. We'll never understand what pre-Big Bang reality was like, or what it was formed of, or why it exploded to create our universe. Such notions are beyond human understanding. But a few unconventional scientists disagree. These physicists theorize that, a moment before the Big Bang, all the mass and energy of the nascent universe was compacted into an incredibly dense, yet finite, speck. Let's call it the seed of a new universe. This seed is thought to have been almost unimaginably tiny, possibly trillions of times smaller than any particle humans have been able to observe. And yet, it's a particle that can spark the production of every other particle, not to mention every galaxy, solar system, planet, and person. If you really want to call something the God particle, this seed seems an ideal fit. So how is such a seed created? One idea, bandied about for several years, notably by Nikodem Poplawski of the University of New Haven, is that the seed of our universe was forged in the ultimate kiln, likely the most extreme environment in all of nature, inside a black hole. It's important to know before we go further that over the last couple of decades, many theoretical physicists have come to believe that our universe is not the only one. Instead, we may be part of the multiverse, an immense array of separate universes, each its own shining orb in the true night sky. That led to another related idea made famous by Stephen Hawking, that each time we create a black hole in our universe, it could give rise to a baby universe that's only accessible to an observer that crosses inside that black hole's event horizon. Then, could our universe actually have been spawned by a black hole that was created in some sort of grand parent universe? And do we give birth to a new universe each time a new black hole is created? If so, what is the reasoning behind these theories? All this and more will be discussed in today's episode. Without an event horizon, there is no black hole. It is the boundary that tells a very different story from an object outside of it versus one inside it. Outside of a black hole's event horizon, any object will experience its gravitational effects, as the space will be curved by the black hole's presence, but it can still escape. If it moves fast enough or accelerates quickly enough in the proper direction, it won't necessarily fall into the black hole, but it could break free of the black hole's gravitational influence. Once an object crosses over to the other side of the event horizon, however, it's immediately doomed to be subsumed into the black hole's central singularity. Because the fabric of space-time is severely curved inside a black hole, an infalling object will reach the singularity within seconds of crossing the event horizon, growing the black hole's mass in the process. To someone located outside the event horizon, the black hole appears to form, gain mass, and grow over time. But what does this have to do with our universe? Well, if you were to take all of the known, measurable forms of matter and radiation in the observable universe, you'd have to add up all of the following. Normal matter, made from protons, neutrons, and electrons, neutrinos, ghostly fundamental particles that rarely interact with normal matter. Dark matter, which dominates the universe's mass, but has so far eluded direct detection efforts, photons, or particles of light, which carry energy from every electromagnetic event throughout cosmic history, and gravitational waves, which are created every time a mass moves and accelerates through the curved fabric of space-time. At the farthest limits of what our instruments can possibly detect, we can see up to about 46 billion light-years away in all directions. If you add up all the energy from all of these forms throughout the entire observable universe, you can arrive at an equivalent mass for the universe using Einstein's most famous relation, E equals mc squared. Then, if you like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is the same as it would be if you compressed any large enough collection of mass or energy into a single point. It would form a black hole. What's remarkable about Einstein's theory of gravity is that if this collection of mass and/or energy isn't charged electrically and isn't rotating or spinning, the total amount of mass is the only factor that determines how large the black hole is, what astrophysicists call Schwarzschild radius. Remarkably, the Schwarzschild radius of a black hole with the mass of all the matter in the observable universe is almost exactly equal to the observed size of the visible universe. That realization, on its own, seems like a remarkable coincidence, raising the question of whether our universe might actually somehow be the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. In the mid-1960s, a discovery revolutionized our concept of the universe. A uniform, omnidirectional bath of low-energy radiation appeared from all locations in the sky. This radiation had the same temperature in all directions, now determined to be 2.725 Kelvin, just a few degrees above absolute zero. The radiation had a practically perfect black-body spectrum, as though it had a hot thermal origin, and appeared identical to within 1 part in 30,000, no matter where you looked in the sky. This radiation, originally called the primeval fireball, and now known as the cosmic microwave background, represented critical evidence that our universe is expanding and cooling because it was hotter and denser in the past. The farther back we extrapolate, the smaller, more uniform, and more compact things were. Going all the way back, this picture of the hot Big Bang appears to approach a singularity, the same condition found at the central interiors of black holes, a location where densities, temperatures, and energies are so extreme that the laws of physics themselves break down. Something remarkable happens when you look at the equations that govern a black hole as well. If you start just outside the event horizon and escape to an infinite distance away from the black hole, you'll find that your distance r goes from r, the Schwarzschild radius, to infinity. On the other hand, if you start just inside the event horizon and track your distance from the black hole to the central singularity, you'll find that same distance r instead goes from r, the Schwarzschild radius, to 0. Big deal, right? No, it actually is a big deal for the following reason. If you examine all the properties of space outside of a black hole's event horizon, from r to infinity, and compare them to all the properties of space inside the black hole's event horizon from r to 0, they are identical at every single point. All you have to do is replace the distance, r, with its reciprocal, 1r, or more accurately, to replace all instances of r with r, and you'll find that the black hole's interior is mathematically identical to the black hole's exterior. It's almost like taking a spherical orb that's 100% reflective, a perfect mirror, and noticing that the entirety of the universe that's located outside of that sphere is now contained, albeit distorted, in the mirror image that's reflected on the sphere's surface. As our understanding of the universe has improved and been refined over the past few decades, 2 new discoveries have rocked the foundations of cosmology. The first was cosmic inflation. Instead of arising from a singularity, it now appears that the universe was set up by a rapid, relentless state of constant, exponential expansion that preceded the hot Big Bang. It's as though there were some sort of field that provided an energy inherent to space itself, causing the universe to inflate, and only when inflation ended did the hot Big Bang begin. The second was dark energy. As the universe expands and becomes less dense, distant galaxies start to recede from us at an accelerating rate. Once again, albeit with a much smaller magnitude, the universe behaves as though there's some sort of energy inherent to space itself, refusing to dilute even as the expansion of space continues. People have speculated that there might be a connection for as long as inflation and dark energy have both been around. The fact that there's a fundamental difference between the expansion rate of the universe that you infer, depending on which of the two classes of methods you use to measure it, only strengthens that conjecture. One potential explanation that stubbornly persists for reconciling this discrepancy is that there was a stronger form of dark energy early on, one that existed after the end of inflation but decayed away before the cosmic microwave background scattered off of the primeval plasma for the final time. Perhaps inflation and dark energy have more in common than we realize, and perhaps black holes will provide a critical insight into the nature of that link. But what might that connection be? Well, once again, black holes could be the answer. Black holes gain mass as material falls into them and decay, losing mass via Hawking radiation. As the size of the event horizon changes, is it possible that this changes the energy inherent to the fabric of space to an observer located inside the event horizon? Is it possible that what we perceive as cosmic inflation marks the creation of our universe from an ultramassive black hole? Is it possible that dark energy is somehow connected to black holes as well? And does this mean that, as astrophysical black holes have formed within our universe, that each one gives rise to its own baby universe somewhere inside of it? These speculations have been around for many decades, and although we lack a definitive or provable conclusion, there are certainly some mathematically compelling pieces of evidence that suggest a link. Nevertheless, many models and ideas abound, and this line of thought continues to be compelling to many who research black holes, thermodynamics and entropy, general relativity, as well as the beginning and end of the universe. Unfortunately, every physical model put forth, at least so far, has failed to make unique predictions that can do the following three things. First, reproduce all the successes, like the already observed phenomena, that the inflationary hot Big Bang has already successfully accounted for. Second, explain and/or account for observed phenomena that the prevailing theory cannot. And last, make new predictions that differ from those predicted by the current leading model, that we can then go out and test. Perhaps the most famous attempt at this is Roger Penrose's conformal cyclic cosmology, in which our universe passes endlessly through a possibly infinite number of cycles, or aeons, each of which starts with a Big Bang and ends with a rapidly expanding empty universe. Penrose's idea makes use of something called a conformal mapping. This is a mapping from one set of coordinates to another, which preserves the angles at which lines meet and the shapes of infinitesimally small objects, but the sizes of objects are not preserved. Conformal mapping, which had previously been in the realm of abstract mathematics, was made popular in the mid-20th century in drawings by the Dutch artist M.C. Escher. If you look at this picture, it shows how an infinite plane can be mapped into a finite area. If we imagine an infinite plane covered in fish of the same size and shape, we can conformally map the infinite plane onto a circle. The boundary of the circle represents infinity. The fish retain their shapes but not their sizes, and get smaller and smaller as the boundary of the circle approaches. Next, let's look at this diagram. It shows how the scale of the universe changes over time. The vertical axis shows time running from Ti equals 0, the exact instant of the Big Bang, to the remote future. The horizontal axis represents the scale of the universe. The diameter of the observable universe we see today is 92 billion light-years. If we extrapolate backwards at the exact instant of the Big Bang 13.8 billion years ago, the diameter of this region would be 0, assuming that the laws of physics still apply at such extreme conditions. If we extrapolate to the far future, then this region will expand exponentially, getting larger and larger. What Penrose does is to conformally map the entire universe from T equals 0 when it has 0 volume to T equals infinity when it has infinite volume. The Escher picture we've seen previously is a conformal mapping of two-dimensional space, whereas Penrose uses a conformal mapping of the 3 spatial dimensions and 1 time dimension. This mapping of 4 dimensions, 3 space and 1 time, cannot be easily drawn in a 2-dimensional drawing, so one of the spatial dimensions is not shown. The diagram shows how Penrose's conformal mapping works. On the left-hand side, we have the picture showing the evolution of the universe. The right-hand side shows a conformal representation of the universe. The conformal mapping is defined so that as the universe expands and its scale increases, its conformal scale remains the same. So, near the Big Bang, the universe is conformally stretched by a large factor, whereas in the remote future, the universe is conformally compressed by a large factor. If we imagine 2 galaxies which are a long distance away from each other, the distance between them will increase over time due to the expansion of the universe. However, the conformal distance between them doesn't change. In addition, although time runs from 0 to infinity, in the conformal mapping, a time of infinity is mapped on to a finite, conformal time. The mathematics of how this is done is much more complex than the conformal mapping of 2 spatial dimensions. If we look at the far future of our universe, after an extremely long time, greater than 10 to the power of 100 years, all massive particles will have decayed. The only particles in the universe will be photons and gravitons. Photons and gravitons have 0 rest mass, travel at the speed of light, and, from Einstein's theory of special relativity, anything traveling at the speed of light does not register the passage of time. So, in a sense, the universe loses track of time. As the universe continues to expand, the density of photons and gravitons falls, and the universe is essentially empty apart from dark energy. Its temperature will get closer and closer to the lowest possible temperature, absolute 0. The clever bit is that if we take Penrose's conformal representation of the far future of the universe, it can be smoothly joined to the conformal representation of the Big Bang at the start of another universe which follows our own. At the point of the join, the distance scale is squashed massively. The very low temperatures and densities of massless particles in the far future of our universe become equivalent to very high temperatures and densities in the new distance scale of the subsequent universe. In addition, Penrose also suggests that this subsequent universe will have the same laws of physics as our universe, and so it too will begin with Big Bang and end with the exponential expansion of a universe containing only massless particles and dark energy. The conformal representation of the far future of the subsequent universe can be smoothly joined to the conformal representation of the Big Bang at the start of another universe which follows it. This next universe will also have the same laws of physics and will also begin with a Big Bang and end with an exponential expansion of a universe containing only massless particles and dark energy. The process can be carried out an infinite number of times. Each cycle of a universe starts with a Big Bang and ends in the exponential expansion of an essentially empty universe, which can be smoothly mapped onto the Big Bang of the following cycle. Penrose calls each cycle an aeon, and all aeons have the same laws of nature, which is why every aeon has the same ultimate fate. This does not mean that all aeons have exactly the same history. The detail of what happens in a particular aeon is due to chance. And in our aeon, after the universe was roughly 9 billion years old, the solar system formed in an outer region of the Milky Way galaxy. The solar system had 8 planets. On the 3rd planet from the Sun, after it had cooled down enough for water to exist in the liquid form, primitive life forms emerged. Eventually, 4 billion years later, intelligent life evolved, which developed into a planet-wide civilization. So, is the conformal cyclic cosmology correct? First off, accept that this theory addresses some of the problems with the standard Big Bang theory, such as, was the Big Bang really a singularity? A place of infinite density where the laws of physics break down? What caused the Big Bang? The mathematics behind the conformal cyclic cosmology is consistent, but that doesn't mean that it reflects the real world. The conformal cyclic cosmology might be an abstract mathematical curiosity, which bears no resemblance to reality. A good scientific theory is one which makes predictions, which can be experimentally tested, and if these predictions are fulfilled, the theory is supported. If not, the theory is falsified. The steady-state theory, in which the universe taken as a whole does not evolve or change over time, was very popular in the late 1940s, and 1950s is a good theory. The theory was shown to be incorrect in the 1960s when it became clear that the universe is changing. Even so, in the words of Stephen Hawking, the steady-state theory was what Karl Popper would call a good scientific theory. It made definite predictions which could be tested by observation and possibly falsified. Unfortunately for the theory, they were falsified. If the conformal cyclic cosmology is correct, Penrose predicts there should be bright spots in the microwave background. These are known as Hawking points and are caused by the evaporation of supermassive black holes in the previous aeon by Hawking radiation. The photons from such evaporating black holes can cross over into our aeon. If these Hawking points were ever found, it would provide strong support for the conformal cyclic cosmology. Another predicted feature is concentric circles caused by the emission of gravitational radiation by the collision of supermassive black holes in the previous aeon. Although some believers of the conformal cyclic cosmology have published scientific papers claiming that such features do exist, the consensus among the vast majority of astronomers who have studied microwave background surveys is that no examples of these features have been found. Previous claims of such detections have been due to errors in the data analysis. Therefore, the general view is that no evidence has been found to support the conformal cyclic cosmology. However, this does not necessarily mean the conformal cyclic cosmology is incorrect. It remains a possibility that such features might exist but could be weaker than we can currently detect. It will be interesting to see how things develop over the next few years. Cosmic inflation is much more widely believed alternative to the conformal cyclic cosmology. After all, as you see, there's a lot to like about the idea that there's a connection between black holes and the birth of universes, from both physical and mathematical points of view. It's plausible that there's a connection between the birth of our universe and the creation of an extremely massive black hole from a universe that existed before our own. It's plausible that every black hole that's been created in our universe has given rise to a new universe within it. Unfortunately, what's missing is the key step of a uniquely identifiable signature that could tell us whether this is the case or not. That's one of the most difficult steps for any theoretical physicist, to determine the imprint of a new idea on our observable universe, distinguishing that new idea from our old, prevailing ones. Until we successfully take that step, work will likely continue on these ideas, but they will only remain speculative hypotheses. We don't know whether our universe was birthed by the creation of a black hole, but at this point, it's a tantalizing possibility that we would be foolish to rule out. Ultimately, what humans can observe of our universe is limited. That's why theories of the universe are never complete. They balance the small sliver of the universe we can observe with mathematical models and theory to fill in the rest. So, in cosmology, scientists search for observable phenomena that disprove their models and reshape their theories again to suit the problem. But as our technology rapidly advances, observations that support or detract from one model or another come more often. And it's completely worth making all this speculation in this work, because we are getting to the point in which this data will arrive. One such observation could produce compelling support for either a cyclic model or confirm the more accepted inflationary theory. Because of how matter is distributed in our view of the oldest part of the universe, gravitational waves that reach us may be polarized, like light, at a particular frequency. Soon, within a few years in fact, scientists may be able to determine whether this polarization exists. If it does, it will support the inflationary model. If this polarization doesn't exist, it will undermine slow contraction, a hallmark of the cyclic model. We'll be one step closer to making sense of time and space, but still on a journey within the cosmos that's far from over. As a small leap, for the first time, astronomers have detected the magnetic fields of massive, blazingly hot stars outside our galaxy. They're stars that actually live in our galactic companions, the Large Magellanic Cloud and the Small Magellanic Cloud. Discovering stellar magnetism in these satellite galaxies of the Milky Way, both of which have a large population of young stars, offers scientists a unique chance to study actively forming stars. It could also answer the question of how much mass a star can pile on before it loses stability. Magnetism is a vital factor in the evolution of massive stars and can also determine how they will end their lives. Stars over 8 times as massive as the Sun leave behind neutron stars or black holes after dying violent supernova deaths that are influenced by each respective star's magnetic fields. Magnetism is also thought to be a key player in the launch of X-ray flashes and gamma-ray bursts that come from dying stars. Located 200,000 and 158,000 light-years from Earth, respectively, the infant stars of the SMC and LMC are believed to lack metals, a term astronomers use for elements heavier than hydrogen and helium. This makes these relatively close stars a good proxy for the first stars to exist in the 13.8 billion-year-old cosmos, which are too distant to study in great detail, even with the instruments we have available. The first generation of stars formed when hydrogen and helium were vastly more abundant than heavier elements across the universe, meaning these initial stars were also metal-poor. Studying these stars can thus help us understand the first chapters of the universe. As research leader Svetlana Hubrig from the Leibniz Institute for Astrophysics Potsdam said in a statement, "Studies of magnetic fields in massive stars and galaxies with young stellar populations provide crucial information on the role of magnetic fields in star formation in the early universe, with star-forming gas not polluted by metals." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.